right, here's our plan for the day. Lecture 13. The first, lecture A is going to involve some things that we've talked about before. Addition rule, conditional probability, the multiplication rule or rules. There's two addition rules as well. And then a little bit new, tree diagram and something called Bayes' rule, which is going to be come up in a more complicated kind of probability problem that you're really going to want to make sure you're paying good attention to. Then we'll take our quiz in lecture B. We'll do more with binomial random variables, which I introduced last time, and Rod Carews, baseball statistics, and an introduction to something called Poisson random variables. That's not poison, okay? It's Poisson. You got to think of it as a French person there. It's not poison, it's Poisson. Maybe it's Poisson, I don't know. I say Poisson. Poisson random variables is another kind of random variable. All right, so first we're doing some quick review. Okay, so thinking hats on here, just think this is all stuff we've seen before, but it would be good to just try to solidify it in your minds. These are things you should know for quizzes. For any two events, A and B, disjoint or not, there's a general multiplication rule that says if you want to find the probability of one or the other happening, or both, this is called an inclusive or, one or the other or both happening. It's not an either or. You find the probability of the first one, add the probability of the second one, and subtract the probability of the third one. I strongly encourage you to think about these kinds of formulas with these Venn diagrams. Again, you can imagine this rectangle is representing the whole sample space. You could imagine it to be like a gym floor or something, and if your sample space involves people, the people stand on the gym floor in certain spots. You've got some event A and some event B, and there could be overlap. To be in the event A or B means you're in one or the other or both, so you are somewhere in there. If you want, I think it's a good idea to imagine the probabilities as representing areas. Imagine the whole box having area 1. That's like the sample space. Think of B as having a certain area. Visually, it looks like perhaps it might be about 0.35 or something. For all of B, by the way. That's all of B. Probability of B might be 0.35. A is, I drew smaller. Maybe the probability of A is 0.25. And their intersection here, what they have in common, A and B, just looking at it visually, that might have a probability of 0.1 or maybe smaller, but I'll say 0.1. What's the probability of being somewhere in here? You do not add all three of these. You can add the first two, 0.25 plus 0.35, but then subtract off the last one. The reason being, if you just do 0.25 plus 0.35, you're double counting the 0.10 because it would occur in A and B. So you have to subtract it off to account for that double counting. 0.25 plus 0.35 is 0.6. The answer here would be 0.5 for the probability of A or B. If you were going to label these different regions with numbers, you'd want to label the interior here, the intersection with 0.1. You'd want to label these moon shapes, crescent moon shapes, with these numbers minus the one in the middle. 0.35 minus 0.1 is 0.25. You want to label that 0.25, and that would be the probability of being in this crescent moon, being in B but not A. And label this one with 0.25 minus 0.1 is 0.15. Okay, so you can also write down, based on this picture, the probability, for example, of being in A and the complement of B, not in B, means you're in this crescent moon, you're at the 0.15 stage right there, for example. You could also figure out the probability of not being in A and not being in B. In other words, you're outside of both of them. All the probabilities have to add up to 1. These are all disjoint regions. So by the summation rule for disjoint events, these would all have to add to 1 because they make up the sample space. these three numbers add up to 0.4, right? 0.5. So the area outside of them has got to be 0.5 as well. 1 minus 0.5 is 0.5. So all those four areas have to add up to 1. They are disjoint. There's no overlap between the regions that I've labeled with probabilities. Okay? It's a nice problem-solving tool. On today's quiz, I said yesterday, you're going to want to use a Venn diagram to help you solve one of the problems. Okay? You can write this with intersection and union notation as well, just for the record. Okay, if you don't want to think about that, then you don't have to. If you've heard of intersection and union in the past, well, it might be helpful to think of it that way too. Here's our crowd probabilities, our chart at least, where we thought about crowd probabilities. I'll put this up for the quiz because you'll need it for today's quiz. Conditional probability notation. Again, never forget this notation here. This represents one number. It's not three separate numbers. A and B are events. They're just symbols, shorthand notation for things that could happen. P is not a number. It's kind of like a function. You say P of A conditioned on B, or more elaborately, say the conditional probability of A given that B has occurred. If you know that B has occurred, what is now your assessment of the chances that A has occurred? That whole symbol represents the one number. That's the probability. And you want to get the notation right. And again, it's called a conditional probability to distinguish it from a regular non-conditional probability. In essence, knowledge that B occurs reduces the sample space. You know you're inside the circle for B. What now is your new assessment of the probability that A occurs? It could be the same. If the events are independent, it'll be the same probability. I'll show you an example with the Venn diagram in a minute. Here's a formula. In fact, let's draw the Venn diagram right now. Two versions of the formula, but they really mean the same thing. The symbols A and B are just symbols. They could be reversed. These two formulas say the exact same thing, just reversing the nature of the symbol, the roles of the symbols. Let me go ahead and redraw that Venn diagram. Although I forgot my probabilities already. Let's see, this was A and this was B. What did I say for B? Point what? 0.35. And what did I say for the probability of A? 0.25. And what did I say for the intersection? 0.1? Okay, so right in there, probability of A and B is 0.1. Let's focus on this one. What's the conditional probability of B occurring if you know that A has occurred? Knowing that A has occurred means you're focused on just this circle. Your sample space has been reduced from the entire gym to just the circle. The question now is, if you know you're in here, what fraction of the probability is made up by this part? That's what this formula is saying. That's 0.1 divided by 0.25. Which would be 10/25 or 2/5. That would reduce to 2/5, which is 0.4. That's not the same as the probability of B, which is 0.35. So in this case, A and B are not independent. If those probabilities were equal, then they would be independent. But knowing that A has occurred increases your assessment of the likelihood that B has occurred. That's the idea. Okay, and again, the Venn diagram can be helpful for thinking that through. Realize that in solving problems, oftentimes the Venn diagram is easier to think about. You should be flexible enough to either draw the Venn diagram to figure it out or use the formula to figure it out. In fact, I'd encourage you to think about it both ways all the time. That'll increase your understanding, increase your problem solving ability. What's next? Well, we mentioned independent events. If A and B are independent, in other words, unrelated, then in conditional probability notation, you can say these two facts are true. this equation and this equation. In other words, the conditional probabilities are the same as the unconditional ones. Knowledge that A has occurred doesn't affect your assessment of the likelihood that B will occur. Knowledge that B has occurred doesn't affect your assessment of the likelihood that A has occurred. Okay? That's the essence of what independence means. And we have the multiplication rule for independent events saying, I'll write it here, the probability of A and B occurring is the probability of A occurring times the probability of B occurring. Looked at a couple applications of this already. We're going to look at the binomial random variable as an application of it today. We did a little bit of that at the end of class last time. That's a special multiplication rule that only works for independent events. Write that down. There's also a general multiplication that works all the time, whether the events are independent or not. And it essentially can be derived by taking the formula for the conditional probability, like this first one, and multiplying both sides by P of A. For independent events, the rule looks like this. For the general multiplication rule, whether A and B are independent or not, you can write these two effects. The probability of A and B occurring is the probability that A occurs times the conditional probability of B occurring if you know A has occurred, or the probability of B occurring times the conditional probability of A occurring if you know that B has occurred. You can think of it either way. It works either way. Nice example to think about with this one is cards. This time draw 2 cards. Okay? Got a well-shuffled deck. You draw 1 card, your friend looks and sees what it is, you don't see what it is. You draw a second card at random, your friend sees what it is, and you don't see what it is. You might wonder, what's the probability that they're both queens? What's the chances of that happening? So A could be that the first one is a queen, and B could be the second one is a queen. You might prefer writing that like this. You could write the formula like this. What's the probability that the first one is a queen? You've got 52 cards, 4 of which are queens. That probability is 4/52. However, for the second one, if you know the first one is a queen, that's not only reduced the size of the sample space to 51 cards instead of 52 cards, it affects how many queens are in the new deck after you've taken the first one out. You have to think about a conditional probability for the second one, because if the first one is a queen, that affects your assessment of the probability that the second one is a queen. It would become 3 out of 51. Three queens left out of 51 cards left. Whatever this product is, 12 out of whatever, 50 times 50 is 2,500. Somebody do that for me? I better not try to do it in my head. Actually, I'll do it. 52 times 51 is 2652. So that probability, which as a decimal turns out to be about, type. About 0.0045, less than a 1/2 of 1% chance. So in over 200 times that you do this experiment of picking 2 cards from a well-shuffled deck, will you get 2 queens? About 1 out of every 200 and, I don't know, 20 times or something. Once out of every 220 times or so. I don't know that the 220 is right, I just guessed. Less than a 1/2 of 1% chance of getting 2 straight queens. That would be an example of the application of the general multiplication rule. Those are not independent events. Knowing you get a queen on the first card affects the chances of getting a queen on the second card. That can be written with intersection notation as well. All right, here's our harder probability problem. Kind of long. Problem solving, when you see a long problem like this, you want to break it into pieces and write down things you know and things you want to find. Testing for a disease. Suppose 0.01% of the population has the dreaded disease A. I couldn't think of a good name. Disease A. That's, 1% is 1 out of 100. 1/100th. 0.1% would be 1 out of 1,000. 0.01% is 0.0001, which is 1/10,000. The probability that a randomly chosen person out of the whole country or world or whatever has disease A is 1 out of 10,000. About 1 out of every 10,000 people has it. There's a test that correctly identifies the presence of disease A 99% of the time in people who are already known to have it. So there are people that are known to have it and people that are known to not have it based on some other test, perhaps. So if there's some other test, why is there a new test? Well, maybe this new test is cheaper. Maybe. That does happen. And correctly identifies the disease as not being present in 98% of the people who are known to not have it. So they're testing this cheaper test to see how well it works. So they take people who are known to have it for some other reason because of some other test, and people who are definitely known not to have it because of some other test. They've got this new test that's cheaper, they're hoping it works well. Sounds like it works pretty well. 99% of the time when somebody's known to have it, this test comes back and says, yes, they have it, it's positive. Positive test, although it's bad for the person, right? And 98% of the time when they're known not to have it, the test comes back negative correctly. Negative meaning they don't have it, so it's good for them. Now imagine you go to a routine checkup with your doctor, and your doctor makes a habit of using this new, cheaper test on his patients since disease A is so deadly, even though it's rare. You go in for your routine checkup, and the test comes back positive. Bad. That's bad, actually. Indicating you have disease A. Or not. Could it be wrong? How worried should you be? Should you get a second test done? Answer these questions based on a probability calculation. Indicating you have disease A. I probably should have said, or not if it's mistaken. Is there a 99% chance you have it? That's what most people would guess, right? They say 99% of the time it correctly identifies people as having it, the disease A, when they are known to have it. However, that's not the answer. This number, this 0.99%, is a probability that the test will come back positive, POS stands for positive, if it is known they have disease A. It's that conditional probability. That's not the conditional probability you want to find, though. You don't know if you have the disease or not. You're not one of that group, in that group of people. The test came back positive for you. You want to find the opposite conditional probability, the probability of having disease A if you know the test came back positive. And the answer is not necessarily 99%. What is it? Nice quick way to try to think about this problem and organize your information is to draw something called a tree diagram. We talked about Venn diagrams last time and how they're a nice problem-solving tool. Today, the focus is on the tree diagram that I'm about to draw. That's a nice problem-solving tool. This tree is going to have some branches. That's why it's called a tree diagram. There are two categories of people in the world, those who have disease A and those who don't. Imagine those who have disease A go up there and those who don't go down here. Of course, many more people are going to go down there than are going to go up there. That's 1 out of every 10,000 people. This is 9,999 out of every 10,000 people. A complement, the opposite of A. These are complementary events having the disease or not. Label these branches with the corresponding probabilities. There's a 0.01% chance that the person has disease, so that probability is 0.0001. Move the decimal place for the 0.01% to the left 2 spots. So you need 3 zeros after the decimal there. 99.99% of them don't have it. The probability of being over here is 0.9999. Pretend everybody in all these groups gets tested. Just pretend that didn't actually happen, but pretend for those people who had disease A, they could get a positive result or a negative result. I won't write negative as NEG, I'll write it as pos complement. That means the negative test result. For those people who don't have disease A, the test still could come back positive or negative. So I write pos and pos complement again. With this diagram, it now turns out to be a good idea to label these branches with conditional probabilities. You've got the people who are known to not have disease, or to have disease A, excuse me, and the test comes back positive. Let me do a lowercase p here, by the way. You don't have to do it in your notes, but I wanted to do it here so I can keep it distinguished from the capital P for probability. For those who are known to have disease A, what is the chance the test comes back positive correctly? That's the 99%, 0.99. What's the chance that the test comes back incorrect? Negative, positive complement. If they are known to have disease A, it's a small chance, 0.01. If it's a 99% chance that it correctly comes back positive, it's a 1% chance that it incorrectly comes back negative. You can do the same kind of thing down here. 98% of the time when people are known to not have the disease, does the test come back negative correctly. That's 0.98. And that means 2% of the time does the test come back incorrect as a positive test result when they don't have the disease. Not quite done. The next good idea in this diagram is to label numbers to the right of these branches that come from the general multiplication rule to, for example, find the unconditional probability that a randomly chosen person in the population has disease A and the test comes back positive when the test is applied to them. These events are not independent. We need the general multiplication rule. Look at the top one here. We can use A as A and pos as B. Based on the fact that I know this conditional probability, when I use that formula, I better use the form that looks like this. Where I put the unconditional probability of A there, and the conditional probability of positive given A, based on what I'm given, what I know. Use that formula. To find that, you just end up multiplying the numbers along each route through the branches. To get to that spot right there, you got to go up this branch and then up this branch. Multiply the numbers along that path. You get 0.0001 times 0.99. Do the same for the other ones. 0.0001 times 0.01. For this one, do 0.9999 times 0.02. In each case, we're really using this general multiplication rule to find the unconditional probability of one thing and the other. Finally, 0.9999 times 0.98. What are those? The first one, 0.0001 times 0.99 Comes out in scientific notation on my calculator, 9.9 times 10 to the negative fifth power is what that means. Real small. 9.9 times 10 to the negative 5. If you write that in standard notation, you need to move the decimal spot 5 places to the left, which means you would have 4 zeros after the decimal. This is 0.000099. The next one, 0.0001 times 0.01 is 1 times 10 to the negative 6, which would be 0.50000001. See if I can reach over the computer here. 0.000001. Next one, 0.9999 times 0.02. Didn't come out in scientific notation. 0.019998. The last one's going to be the biggest. These all have to add up to 1, by the way. These numbers on the far right have to add up to 1. But we can also do the last one as 0.9999 times 0.98. 0.979902. 0.979902. Still not quite done. We've made our tree diagram. What do we do with it? It was fun to make, but what do we do with it? We want to find now again the probability that you have disease A if it is given that it's positive. The doctor says the test came back positive. What are the chances you have disease A? Use the formula for conditional probability, which can be written like this. In this context, remember it's the probability of the second one that goes on the bottom. We know the top, we just figured it out. It's that number right there. 0.000099. That's the top. What about the bottom? What's the probability that it's positive? I hope it's intuitive, so I'll show you a formula that you would add up this number and that number for the bottom. Because it can be positive in 2 ways that are disjoint. The person could have disease A and it could be positive, or the person could not have disease A and it could be a positive test. The bottom, by the addition rule for disjoint events, is the sum of these 2 numbers, 0.000099 plus 0.019998. We're almost done. You can add up the numbers on the bottom. I'll just do it on the calculator. 0.000099 plus 0.019998. The number on the bottom is 0.020097. Now take the top, 0.000099, and divide by that number on the bottom, which I can do like this. On the calculator, refer to the previous answer. And guess what? This answer is not very big. 0.0049. Less than a 1/2 of 1% chance. What? You have a very small chance of having disease A, even though the test came back positive. How could that be? I thought the test was good. This is not wrong. This is correct. You definitely should get a second opinion. You should get a second test, maybe that more expensive test. This comes out to 0.0049, about a 0.5% chance, 1/2 of 1%. In other words, of every 200 people that get this cheaper test, if it comes back positive, only one of them has disease A, most likely. Doesn't that sound crazy? How can that be? It's 99% accurate, I thought, or maybe 98% accurate. Well, without getting into too much detail, because it's about time for the quiz, intuitively, the reason why this happened is because the prevalence of the disease in the whole society, the whole country, the whole world is so small. Only 1 out of every 10,000 people have. Your probability did go up. Okay, before you got the test, you only had a 1 out of 10,000 chance of having the disease. After having the test, your probability went up to about 1 out of 200. But it's still a probability, small probability, so you should still get a second opinion. You should still get the second test, a more expensive test. So a cheaper test that comes back positive like this, but maybe is less trustworthy than the more expensive test, should not be taken to say you have the disease. What it should be taken to mean is you should probably get the more expensive test. You still might have a very small chance of having it. Okay? So it's kind of surprising. What we just really illustrated here is something called Bayes' rule. And here it is in general form. Kind of a crazy looking formula. You can look at that and enjoy it for the moment, but we're going to take the quiz, so you want to put things away. I'll put it back up after the quiz.